This is X4, questions 4 and 5, which are kind of IDS and A search. So both informed search and uninformed search. But anyways, I'm going to do both of them at the same time. So the question is about IDS, and we have 188 states, and the question is it is asking about how to realize that the goal doesn't exist as quickly as possible. So first, IDS is searching the root, and then searching root plus level 1, searching root plus level 2, searching root plus level 3, and so on. So if you have many levels, if the tree is kind of deep, then it's the same thing, like this, the same subtree is repeated many times. So we don't want that. We want a tree with a level that's as small as possible. So we want small number of levels. And in particular, the smallest possible number of levels will be 2, because we have more than one state, so we have a root, and then there can only be one root, and everything else should be in level 1. So that's our intuition. So that's the root, and then everything else, which means 187 of the other states. If all of them are in level 1, then we only need to repeat the root once. So of course, in IDS, we search everything up to level 0, up to level 1. Up to level 0, of course, there's only one root. Up to level 1, there is the root plus everything, so 188. So in total, we just repeated the root. So the total number of nodes or states that we searched will be 189. And next is the A search in a maze, and we start from state 0, so we probably need to keep track of the queue, the priority queue, which will be very long, but let's do that. G and H and G plus H. So at the beginning, we haven't incurred any cost yet, so G is 0. So G again is the cost so far, and H is the kind of the predicted cost that we will incur. Here, the heuristic is the Manhattan distance, so it's actually the correct distance, right? Because if we want to move from 0 to 8, we actually need 1, 2, 3, 4. So we need 4 steps. Because there are no walls in this maze, we are literally just so the Manhattan distance is just the cost. So that's 4, and you'll notice that since there are no walls, we are just doing tie breaking, because if you start from any state, the total cost should be exactly the same. And the tie breaking is with a smaller index. We don't have that yet, so let's do it. Let's see, 1 and 3. So starting from 0, you can move to the right, you can move down. So we get 1 and 3. So the distance so far is just 1, you just moved 1 step, and 3 the same, and 1, you need to move 1, 2, 3, so the remaining number of steps is 3, and the same thing for 3. So you will notice that all of these are just 4. Okay, next, get rid of 1 because of the tie breaking rule. Again, all of them are tied, so we just keep expanding the thing with smaller index. So we get to 1. From 1, we can move to 2 and 4. The bad news is 1 can actually go back to 0. So there are 2 ways of doing this. In the programming homework, you should not be going back, because going back is not a good idea in general. But here, I'm going to write down the version with the going back, and you will see that it doesn't matter. So we'll add 0, because 0 is already removed. So we need to add a new 0. And the cost will be going to 1 and then go back. So that would be 2. And when we go back, the cost becomes 4. So that's 6. And then the other two are 2 and 4, which, as I said, it will just be tie breaking. So we are expecting all of these to be 4. Let's check. 2 from 1, we already incurred a cost of 1. From 1 to 2 is just one step, so it's just add 1. So if you are doing these maze questions, computing trees are actually very easy. Wherever you came from, that cost plus 1 is your current cost. So the same thing happens here. And then you need to compute the distance from 2 to 8, which is 2, and 4 to 8, which is like 1 and 2 as well. So yes, we are just doing tie breaking. Okay, next. Are we going to expand 0? No, because the 6 is larger than 4, so we're not doing tie breaking if there are no ties. I mean, so the tie breaking is between 2, 3, and 4, so get rid of 2. We're going to get 2 can go back to 1, and 2 can go to 5. So if 2 goes back to 1, then it's just, again, wherever we came from, add 1. And the 1 for 1 is 3, so it's 6. So again, we're never going to get to that anyways. And 5, we have, again, 2 plus 1 is 3, and remaining there's only one step, so it's 4. So you can probably see the pattern. We are going to add all of these things back, but we're never going to use them. So next, let's continue this process. Where are we? There are some 4s, and the one with the smallest index will be 3. And then from 3, we're going to add 4 and 6. So 4 and 6, we have 4 already. And actually, if you compute the cost, it's also 2 plus 2. So 4 is just replace this 4 with exactly the same cost. And 6 is actually a new one. We're going to put in 2, and then 2 steps left, so that'll be 4. I think at this point you don't need to keep going. You already observed the pattern, but let's just do one more step. And among the 4s, there are 4, 5, and 6, so of course we're going to do 4. And then we're going to add 5, which is the same, add 1, again 6, and add 7, that's the new thing. And add 3 is, okay, 3 is dropped, so we need to add it back. But in any case, 7, we are starting from 4, right? So that's 2, 2 plus 1 is 3, and 7 is very close, so again it's 4. Just tie breaking. And 3 going back, well, we're at 4, and then we're adding 1, and then 3, the remaining number of steps is 3, so it's 6 again. Alright, so what are the 4s now? 5 and 7, I mean 5, 6, and 7, so get rid of 5, and then we are finally adding 8. So that's 4 steps. It's just 0. Manhattan distance to itself is 0, so it's 4, and 5 can go back to 2. Okay, that's way too much. We need to add back 2 and 4 back from 5, and you know what will happen. It's just like 6, so I'm not going to write them down. So let me just put it here as 2 and 4, and the g plus h, both of them will be 6 back from 5. And at the end, just get rid of 6, and you get 3 back. Okay, so 3 is there, so just replace the 3, and then where are we? 7, and we have 7 already, so that's good news. And 7 just replace the 7. I mean they have the same cost anyways. And then next just remove 7, and then we get 6, 4, and 8 back. Where is 6? 6 is removed. unfortunately. So add 6 back. 4 is there, nothing changed, and 8 is here, so that's great. And finally, wow, finally, we remove 8, and then that's uh, just tie breaking. Right, so it's just 0, 1, 2, 3, 4, 5, 6, 7, and 8. So again, the whole thing is just tie breaking. And if I change this using the larger index, then the question may be like slightly more interesting, but this one is really not.